Okay, guys, any questions so far? Producer consumers, System 5 semaphores. We haven't seen any examples of System 5 semaphores yet, but as you have seen, they provide us with the very important functionalities. Okay, so no questions, I guess. So we will continue with the dining philosophers. Now, this is already an example that you have seen in the context of the OS course, so I'm not going to get into too much detail, but rather on how to solve it, basically. Not the problem itself, but how to solve it using POSIX and System 5 semaphores. Now, for the remaining problems, I will try to give you the solution using both POSIX semaphores and System 5 semaphores, using both of them. Now, and you will see firsthand that the answer is usually much simpler with System 5 semaphores and quite complex when it comes to POSIX semaphores. Now, the dining philosophers is, of course, a classic synchronization problem introduced by, of course, the great computer scientist Edgar Dijkstra. So we have supposedly 5 philosophers sitting around the dinner table, and depending on where you read this from, sometimes they are eating sushi, sometimes they are eating pasta, depending on the country that published the book. And there is a fork in between each pair of adjacent philosophers. Now, in order to eat, for some reason, a philosopher needs to pick up 2 forks that lie at the philosopher's left and right sides. So if each philosopher is a process, that means the process needs 2 resources. Each process needs 2 resources in order to carry out the operation that it wants to complete. Now, the philosophers that just keep on philosophizing and eating. They eat a bit, they think a bit, eat again, think again, and so on. So we have non-critical sections about thinking. Each philosopher can think on its own. And we have the critical sections, which is eating. Why critical section? Because they are manipulating shared resources. What is the shared resource? The shared resource are the forks. We have 5 philosophers, 5 forks, and each philosopher needs 2 forks in order to eat. So they need to share those forks. That means there is a synchronization problem here, regardless of whether you use processes or threads. Now, the forks are our shared resource, and of course, you need to have semaphores in order to protect them. So you need 1 semaphore in order to protect each of them. 5 forks, 5 semaphores. Now, a first clumsy attempt at solving this problem, of course, could be the following, the straightforward approach. Any of these processes, let's say process 2, right here, which needs fork 2 and fork 3. So it first thinks, so this is the non-critical section. Then it must get the shared resources. So it calls wait F2 in order to get the first resource, wait F3 in order to get the second resource. Then it is inside the critical section, so it eats. And once it is done, in order to get outside of it, it will put down the forks. So it will call post on both F2 and F3. Now, of course, this is a very clumsy approach. What can go wrong here? Who can tell me? I'm checking whether you're there. What can go wrong?
The sequential weights feels like non-atomic.
Well, not only it feels like, I mean, it is definitely not atomic. You have 2 separate statements, so they are definitely not atomic. Definitely not atomic. So there can be a context switch between the 2 weights. There can be a context switch between the 2 weights, and that, of course, would be disastrous for us. So let's say, for instance, P0 calls weight F0, and there is a context switch, and then P1 calls weight F1, and there is a context switch, and P2 calls weight F2. So basically, each philosopher is taking the fork that is to the right of them, sağlarında olan çatalı alıyorlar. And now every philosopher has 1 fork, and nobody can eat, because they need 2 forks in order to eat. So even though we had 5 forks on the table, and so that means by 2 forks per person, at least 2 philosophers could be eating, in this scenario, nobody can eat. So the question is, how do you make sure that each philosopher either gets both forks or none of the forks? Ya ikisini de alacak ya da hiçbirini almayacak. That's the question. How do you accomplish that? Using POSIX semaphores or using System 5 semaphores. That's the whole idea. Now, this is very easy to solve with the System 5 semaphores. Well, all you have to do is just call atomically wait on both semaphores. So we will call wait on both the semaphore representing the fork to our right and on the semaphore representing the fork to our left. So either we will call wait and succeed in acquiring both of these semaphores, so both of these forks, or none of these forks. So if we can get both of them, semop will return. If we cannot take both of them, semop will be blocked. It's very easy. So if you want to get the forks for philosopher I from 0 to 4, so for the ith philosopher, we need two operations, one for the left fork and one for the right fork. So we need which semaphores? The ith semaphore and the I plus 1 modulo 5 semaphore. So 0 and 1, 1 and 2, 2 and 3, 4 and 0, and so on. And what are we going to do with them? Well, very simply, we are going to decrement them, -1. So we are performing a wait operation. And the flag is set to 0. We do not want anything special. And we simply call semop forks ops2. So we have two operations. Here are the operations. And this is the identifier returned by semget, representing the set of the semaphores. And here are the set. So IPC private, so a random identifier with 5 semaphores in our set. Created. And if that set already exists, it will return an error. So IPC create and IPC exclusive, same idea as in the files. Any questions about this? Any questions about the System 5 solution? As you can see, it's not really that complicated. Just call wait on two semaphores atomically together. Now, you can do this with System 5, but unfortunately, you cannot call atomic wait on multiple semaphores with POSIX. So now let's look at what is going on with POSIX semaphores, how you can solve it with POSIX semaphores. Now, here you need help. You need help. We need help. We need some help. Now, this help usually appears in the form of additional semaphores, in the form of additional processes. That's how usually POSIX semaphores manage to solve these complicated synchronization problems, by using more semaphores, more processes, more data structures in order to figure it out. Sometimes it is relatively simple, and sometimes it is not, unfortunately for you. But then again, the POSIX API is simple and it is more portable. Now, if we had only 4 philosophers at the table at any time, it would be impossible to have a deadlock. Why impossible? Well, it would be impossible because since you have 4 philosophers, if there are only 4 philosophers, then in the worst case, where each one picks up a fork, since there are 5 forks, at least one philosopher will still be able to continue to eat. So the system will not block. And after it eats, it will put down the 2 forks and somebody else will be able to continue. So if we had 4 philosophers, the system would never block. The system will never deadlock. Okay. Now, the number of philosophers, however, is not 4. It is 5. However, we can control implicitly, dolaylı bir şekilde, the number of philosophers at the table with a semaphore named footman, initialized to 4. This is a pattern, in fact, a synchronization pattern. For those of you who have already taken design patterns, you will know that this is a category just like creational, behavioral, structural patterns. So multiplex pattern is a type of concurrency pattern, a template solution that you can use in order to solve this kind of problems. We will talk about that more when you take the course of object-oriented analysis and design. Now, this footman is an additional semaphore, and it is initialized to 4. Now, how does it work? Let's say that getForks is called by process I. So what does it do? This process first calls wait footman. So bunu garson gibi düşünebilirsiniz arkadaşlar. So some kind of a waiter. It is initialized to 4. So 4 is reduced to 3 after the weight. And then this process tries to lake the left fork and the right fork. Now, maybe it will take both of them, or maybe it will take only one of them. Is there a case where it takes only one of them? Now, since footman is initialized to 4, since this initialized to 4, that means only 4 philosophers can execute, which means it is guaranteed that there are 5 forks available for 4 processes, which means there will never be a deadlock. So at least one of the processes that called get forks will be able to execute both of these weights. Both of them. So we are using footman in order to throttle, kontrol etmek için, kontrol altına almak için, in order to throttle the number of philosophers, the number of processes actively competing. Kendi aralarında çatallar için yarışan süreçlerin sayısını kısıtlamak için dolaylı bir şekilde footman'ı kullanmış olduk. Now, since footman is set to 4, that means the 5th process, whichever it is, that will call get forks, will be stuck at wait footman. And it will never touch the forks. So that means it is guaranteed that we have 5 forks for 4 processes, thus guaranteeing that there will never be a deadlock. And of course, in the case of putting down the forks, it works in reverse as a mirror of the get forks function. Now, who is going to be the process, the unfortunate process that will be stuck at wait footman? Well, it will be a random process. It is up to the kernel to decide who gets to eat or not. Now, this solution also guarantees that no philosopher starves. Imagine that you are sitting at the table and both of your neighbors are eating. You are blocked,
Sir,
waiting for your right fork. Yes?
I am sorry, but I couldn't comprehend what the footman does, really. Can you go over it again?
The footman throttles the number of processes. It limits the number of processes actively competing for the resources. Now, normally you have 5 processes. We have 5 philosophers. 5 philosophers, 5 processes. Each of them want to obtain 2 forks. Thanks to footman, which is initialized to 4, we are making sure that one of those philosophers will not be able to compete for the forks.
Okay, I see.
Only 4 of them will be able to compete. And since we have 4 processes competing for 5 forks, well, that means at least one of them, at least one, maybe 2, at least one will be able to definitely get 2 forks, since we have 5 for 4 processes. Now, this solution, however, also guarantees that no philosopher starves. So no philosopher is left without ever eating. How? Imagine that you're sitting at the table and both of your neighbors are eating. So you are the unfortunate process that was stuck at wait footman. Now you are blocked waiting for your right fork. Now eventually, your right neighbor will put it down because eat cannot run forever. And since you are the only thread process waiting for that fork, you will necessarily get it next. And by a similar argument, you cannot starve waiting for your left fork. So eventually, everyone will get a chance to eat. So you cannot have the pathological scenario where always the same process gets stuck waiting for the footman. Anlatabildim mi arkadaşlar? Soru var mı? I mean, you can see the difference between POSIX and System 5. In System 5, it was just done. You want 2, take 2. You want 3, take 3. With POSIX, you need an additional semaphore and additional processes and whatever. Well, this is the cost of portability. Okay. And that brings us to our last example for today. And that is the cigarette smokers from 1971. Another classic problem. It appears with multiple names Sometimes it's called cigarette smokers. Sometimes it is called the baker's problem. Tatlıcılar, fırıncılar falan filan. It has multiple versions. Now, this is the most classic one. There is also a Wikipedia page about it where you can find more details. Now, the idea is simple. Now, this is an example from the time when smoking was not criticized. So nowadays, I mean, it is, of course, a very bad habit. But at those times, well, people were smoking next to children. They were smoking inside cars. Those were difficult times. I am very lucky for you. I am happy for you that you have not gone through that period, because I remember I remember having to travel in buses from one city to the other in the 80s, especially, and people were smoking inside the bus. Imagine having to go from Istanbul to Ankara, from Istanbul to Samsun, to Izmir or whatever, and people are smoking inside the bus, many people. And you just have to breathe that, inhale that. And there's nothing you can do because smoking is allowed. Difficult times, especially for non-smokers. Sorry. Now, what's the issue with the cigarette smokers? Now, 1971, this problem appeared, and it is different. It is different from the dining philosophers. It is different from the producer-consumer. How is it different? Assume a cigarette requires 3 ingredients to make and smoke. So you need 3 things in order to make a product: tobacco, paper, and matches. And we have just three smokers around a table, each of whom, has an infinite supply of one of the ingredients. So you have 3 smokers. They all want to make cigarettes in order to smoke. And each of them has one material in infinite amount. One of them has infinite tobacco. One of them has infinite paper. And the other one has infinite matches. Okay. There is also a 4th actor, a non-smoking agent. Now, this agent enables the smokers to make their cigarettes. And this agent arbitrarily, so randomly, basically, selects 2 supplies to bring to the table. So every once in a while, the agent comes to the table where the smokers are sitting and drops to the table 2 supplies, maybe 2 different supplies, maybe tobacco and paper. Maybe it brings paper and matches, maybe tobacco and matches. So that means the smoker who has the 3rd supply should remove the 2 items from the table, using them along with their own supply to make a cigarette, which they smoke for a while. So let's say that the agent brought tobacco and paper. So that means the smoker who has an infinite amount of matches can take the tobacco, can take the paper, and since that person now has all 3 ingredients, that person can now make a cigarette and smoke it. Okay. Once the smoker has finished his cigarette, smoking it, the agent comes again. After the smoking is finished, the agent comes again and brings 2 new supplies to the table. 2 different and new supplies to the table. And this goes on forever. So the agent keeps coming. One smoker takes the resources, makes a cigarette and smokes. The agent comes again. Once again, there is a smoker making a cigarette and smoking again and again and again ad infinitum, for infinity. Now, the ingredients here are the resources, the ingredients that the agent is bringing to the table. So we'll need to protect them. So we'll need to have one semaphore for each. And I believe that you can guess what can go wrong in this scenario. Now, do you have any questions so far about the premise, about the problem itself? Have you seen this in the operating system course?
I do not remember it, no.
Last year, yes.
Sorry?
In the times I had the course before, yes.
Okay.
Maybe I missed it.
So this is the visual representation of the problem. So we have 3 smokers, 1 agent. The agent just puts the ingredients, lets know the smokers that the ingredient is available, waits for the table to be cleared, and then brings again ingredients to the table. Whereas the smoker waits for the ingredients, 2 ingredients, each smoker, takes the ingredients, which means the table is available, so that the agent can bring new ingredients and smokes for a while. This is the whole idea. The question is how to make this work like a well-oiled engine as efficiently as possible. Now, a first clumsy attempt that doesn't work. So let's say that we have a semaphore representing the agent, so the waiting for the table, basically. And we have 3 semaphores, one for each supply. So we have the tobacco, paper, and matches, all initialized to 0. Why 0? Because initially there isn't any on the table. So let's say that this is the smoker who has an infinite amount of matches. So in an infinite loop, it waits for, well, since it has matches, it will wait for tobacco and paper. So it waits for tobacco and paper. Once they have been delivered, it gets the ingredient, so it is inside the critical section. It smokes it, and then it lets know the agent semaphore that it is done. So I have smoked it, and now the table is available, and you can bring new ingredients. And the agent, on the other hand, in an infinite loop, it waits to be notified that the table is available. And when it is notified, so when it completes the wait statement, it brings 2 random ingredients, maybe paper and tobacco, maybe matches and paper, maybe tobacco and matches, and so on. So what can go wrong? Who can tell me?
Maybe he gets wrong one.
Wrong what?
For example, person has paper and agent gets paper and match, for example.
Well, this person, for instance, this smoker has matches, but it is not asking for matches. So there is no case that the smoker has matches will get matches. Each smoker is trying to obtain the 2 supplies that are missing from them. So would this work? I mean, if we had 3 processes like this, of course, with different supplies. So one will be waiting for tobacco and paper, the other one will be waiting for paper and matches, and the other one will be waiting for matches and tobacco. And we have one agent. Would that work? Synchronization-wise? Or do you see a problem?
Is it too bad if we think it seems fine?
There is a bit of an echo on your system, Mr. Alp. This will lead to a deadlock. I'm just asking you how it will lead to a deadlock. This solution is insufficient.
I think critical section is not protected.
Why? How? How is it not protected?
I mean, it wants tobacco and paper.
Okay.
And meanwhile, agent. No, actually, is it? No, I'm confused right now.
Okay.
Sir,
Yes.
this could be the situation. One process wants tobacco and matches, and get this critical section and get the tobacco, and it should wait for matches. So it has tobacco but no matches. The other process needs tobacco and paper and get into this, but tobacco has already taken, so it couldn't get tobacco, so it will not be able to take paper also.
Yes, Mr. Krishna. That's exactly what could go wrong. So remember that you have one smoker, you have 3 smokers in total, and you have one smoker for each combination of missing supplies. So you have one smoker that waits for tobacco and paper. You have another smoker waiting for paper and matches, and another smoker waiting for matches and tobacco. So the agent now has brought paper and tobacco. Okay. So normally, only the smoker that has matches can make a cigarette. So it tries to get the tobacco, very nice. And just while it is about to get the paper, the other smoker that needs, for instance, paper and matches, he takes the paper. Now, the other smoker needs also matches, but there are no matches. This smoker needs paper, but he cannot take the paper because the other smoker got the paper. So nobody can smoke now. The agent is waiting for the table to be cleared. The two smokers are waiting for additional supplies. Everybody is waiting. Deadlock. Mr. Anil also says the smoker has matches, gets a tobacco, context switch, smoker has tobacco, gets the paper and deadlock. Yes, yes, Mr. Anil. Yeah. As you can see here. Of course, nobody will be able to smoke, which is good for the smokers, but it is very bad for the system. So long story short, very, very similarly to the case of dining philosophers, we have processes that need multiple resources, and they must either get all of them or none of them. Now with system 5 semaphores, system V, this is very easy to solve, no problem. Very simply, you just have a weight, a compound weight with two semaphores, and each smoker simply calls a weight for two semaphores. So either it will get both of them, or it will keep on waiting. As simple as that, and you're done. So with system 5, the algorithm is just 5 lines. But let's look at the POSIX case now. Any questions about the system 5 solution? Okay, so all you need is a SEMOP with two operations, just like in the case of dining philosophers. Now POSIX. İnsanları POSIX'ten soğutacağız bu şekilde. Evet. This is a bit messy. This is a bit messy. So we will need 3 additional processes in order to solve this. So we have 3 smokers, 1 agent, 4 processes. So we need 3 more processes called the pushers, iticiler, that will respond to the signals from the agent and keep track of the available ingredients. And of course, signal the appropriate smoker. Now, do not be fooled that I say signal. These are not actual signals. We're talking about semaphores, not the signals that we saw. So how is this going to work? Now, this is a good example in order to show you how complicated things can get when you do not have access to multiple atomic operations. Okay, but it is solvable. It is still solvable. Let's see how. So you have flags. Okay, so these are just flag variables. Is match, is tobacco, is paper, set to 0. Okay, now what do they mean? What's the meaning of these flags? We have semaphores. How many? 6. We have 6 semaphores. 3 for the pusher processes and 3 for the smoker processes. Now, we also have the agent semaphore, which is set to 1 in order to signal to the agent when to come to the table or not. Now, the 3 semaphores are initialized to 0, tobacco, paper, matches. And the other 3, tobacco 2, paper 2, matches 2, are also initialized to 0. And we also have a mutex M in order to achieve protected access. Wow. That's a lot of semaphores for a relatively simple problem. Now, the Boolean variables, is match, is tobacco, and is paper, they indicate whether or not an ingredient is on the table. So these variables, they indicate whether a resource is on the table or not on the table. And the pushers, they use tobacco 2, paper 2, and matches 2 in order to signal the smoker. So for instance, they will use tobacco 2 in order to notify the smoker who has tobacco, or the other semaphores likewise. So the pushers will use paper 2 in order to notify the smoker with paper. Now, what's the idea? How does this work? The idea is very simple. We are setting up the system in such a way that the additional processes, those 3 processes, they will check what is on the table, and they will directly notify with a single post directly the process that is waiting for that combination. That's the strategy that we're going to use here. That is, in general, the strategy that is used in POSIX. I mean, you can only wake up a single process with your post, so we are going to exploit that. Arkadaşlar tekrarlıyorum bu kısmı. The strategy, genel yaklaşım bu noktadan çözebilmek için bu birden fazla öz kaynağı tekil bir şekilde, atomik bir şekilde alma problemini ek süreçler kullanıyoruz bu bağlamda. Neyi başarıyoruz bununla? Amacımız öyle bir yapı kuralım ki nokta atış tek bir post ile hangi kombinasyonu, işte şunu ve şunu, işte yok kağıt ve kibrit, yok kibrit ve tütün. Hangi kombinasyonu kim bekliyorsa nokta atış çat diye onu uyandıralım. Eğer sadece o uyanıyorsa iki tane sürecin uyanıp da birinin onu alma ihtimali yok. Taktik bu. So the strategy is very simple. We set up the system in such a way that the pushers will notify only and directly the process that is waiting for the right combination of supplies. And since only one process will be notified of them, well, there is no chance of having two processes simultaneously, one of them taking this and the other one taking that. That's the whole idea. I mean, it is simple on paper, but let's see the contents of these processes. Right now, we have 7 processes: 1 agent, 3 pushers, and 3 smokers. And all that for what? So that the 3 smokers can smoke. It's unbelievable. Okay. Let's look at the pusher. How is the pusher implemented? Now, this pusher, so remember, we have 3 of them. So this pusher wakes up anytime there is tobacco on the table. So if the agent has brought tobacco and paper or tobacco and matches, this pusher will wake up whenever there is tobacco on the table. Okay. So what happens if there is tobacco on the table? So that means if there is tobacco on the table, either there is tobacco and paper or tobacco and matches. So one of the smokers will get to wake up. But which one? So pusher A waits and sleeps until there is tobacco on the table. If it succeeds in wake tobacco, that means there is definitely tobacco on the table. Then it gets the lock. It is going to access a shared resource, so wait M. So it checks the flag variables. This is where they come in. So if this paper is true, it knows that pusher B has already run. Okay, so this is used in order to understand which other pusher has been already executed. Now, if this paper is true, that means pusher B, which was waiting for paper, has already run. And it calls post matches. It signals the smoker with the matches, which means that in that case, why is it the signal the smoker with the matches? It set its paper to false. No, it's correct. Okay. And then it signals the smoker with the matches. Now, similarly, if it finds a match on the table, of course, it can signal the smoker with the paper. Now you need to see the additional pushers in order to understand what is going on in this case. Now, let's look at them all together, all 3 of the pushers simultaneously. Wait tobacco, wait paper, and wait matches. Each of them is checking each other. Each of them, when every pusher wakes up, it checks whether the other pusher has been executed or not, in order to figure out, in order to understand which pair of materials is present on the table. Birbirlerine bakıyorlar. Hangisi çalışmış ki anlamaya çalışıyor. Ya biri anlıyor, ben çalıştım tamam diyor, ama başka diyor ki biri çalıştı mı? Bakıyor ki anlasın hangi 2 malzeme var masanın üzerinde şu anda ki ona göre nokta atış tam onları bekleyeni uyandırsın. Now, we will get back here. Let's look at the smokers and the agent. Now, let's look at this. The agent brings paper and matches. The agent has brought paper and matches. Now, can any of the smokers execute? No. The smokers are waiting for tobacco 2, paper 2, matches 2. So this is the smoker that has an infinite amount of matches. This is the smoker that has an infinite amount of paper. This is the smoker that has an infinite amount of tobacco. Okay, so they are all waiting. First, the agent has brought the ingredients. The agent has brought, why not? It has brought paper and matches, which means the pusher waiting for paper and the pusher waiting for matches will execute. Maybe pusher B will execute before pusher C, or maybe pusher C will execute before pusher B. We don't know that. Let's say pusher B executes before pusher C. Now, there is paper and matches, so the wait will succeed. It will get the lock. Now it checks the variables. Now, is tobacco true? No, it's not true. Why should it be true? They are all false. Is match true? No, it's not true. Why should it be true? They are all initialized to false. So that means else it will set is paper to true. Okay, now is paper is true. It will let the lock go since it was modifying the variables. And that's it. Now pusher C will get a chance to execute, which was also waiting for matches, but it was stuck at wait M because pusher B got to execute it first. So pusher C will get inside and it will check. Is tobacco true? No, it's not true. Is paper true? Yes, it is true. We just set it to true here. Well, that means if is paper is true, that means there is paper on the table. But since we have also succeeded with wait matches, that means there is also matches on the table, which means we must wake up the smoker who has an infinite amount of tobacco. And so we wake up the smoker with the infinite amount of tobacco, post M, and that's it. And the smoker with the infinite amount of tobacco wakes up, certain that there is paper and matches on the table, gets the ingredients, he smokes, and then lets the agent know that the table is free to bring in new ingredients. Anlatabildim mi arkadaşlar? Soru var mı? Buyurun sorun. So it's understood, it's clear. So you can solve a midterm like this. Peki arkadaşlar. Madem soru yok. Efendim, sorun var. Bir ses geliyor bir yerlerden ama.
No, I wanted to say that it's clear now, but when it comes to midterm, it all mixed up.
Okay. Mr. Alp says the agent in this slide is only an example, right? It could be posting other things too. You mean different types of supplies? I mean, the agent will always wait agent SAM, of course, in order to be notified when the table is ready, but it will post always a random couple of distinct supplies. So it will run and post paper and matches. In the next round, it will post paper and tobacco. In the next round, maybe it will post paper and matches again. Maybe it will post tobacco and paper again and again and again. But every time, a random couple of distinct supplies. Yeah. So these are all supposed to be running in an infinite loop. I didn't put the while true in order not to confuse you.
So these flags in the pushers,
Yes.
can we think them as shared memory objects?
You should definitely think of them as shared memory objects.
Okay.
Because otherwise, how are the pushers going to access them? Since every pusher is a distinct process.
Yeah, that's right.
Yep. But you do not have to worry about where to store the semaphores. So the System 5 semaphores, for instance, they are manipulated, they are stored in kernel space. But if you're using, as in this case, POSIX semaphores, and you are using unnamed semaphores, well, in that case, they also need to be stored in shared memory. Obviously. Yep. So class, I mean, this gives you an idea of what is happening in the world of POSIX semaphores. So you can still solve this type of problems where you need to decrement and increment atomically when you need multiple resources. But as you can see, it requires quite a bit of thinking, But then again, you avoid the complex API of System 5 semaphores. Now, this will be the last thing for today, the synchronization barrier, which you have already seen in the case of signals. Remember, we had used pipes in order to solve it, the synchronization barrier. Now let's look at the official explanation, how to solve it with semaphores. Now the synchronization barrier is also often encountered, also a quite often, frequently encountered problem, where you have multiple processes or threads even. And the idea is that the problem is that we want all of them to first reach a certain problem, to first reach a certain point in their execution before going further. Hepsi belli bir noktaya kadar gelsin ve ancak o zaman daha öteye geçsinler. That's why it is called a barrier. We want all of them to terminate a certain amount of things, and only after that should they be allowed to continue. That's the idea. So you can have, for instance, a worker processes and a boss process. So the boss process, for instance, will not pay their salary unless all the workers have completed the required task. Or, for instance, you can have a teaching assistant process and student processes. And the student processes, they agree to, in the middle of an exam, to give their papers to the TA, but only after all of them have finished. That's a synchronization barrier. I mean, in fact, this is one of the questions that I had used in an exam some years ago. So how do you solve this? It's very easy. You see, it's much easier than using signals or pipes. So here, for instance, you have the boss who is doing some preparations, whatever, doesn't matter. And you have the workers. So the workers, they have to all finish their work before having their salaries paid. Now, all of them must reach this point, finish the first stage of their work before continuing with the second stage. Now, it doesn't matter what the example basically entails. The idea is, how do you make sure that all of the processes reach a certain point, all of them, and before any of them continues any further? Now, you can solve it, of course, with POSIX semaphores or System 5 semaphores. With System 5 semaphores, very easy, as usual. You have a single semaphore, and it is initialized at n. Okay, so every process or thread, whatever it is, reaching the rendezvous point, will call wait on it, and then wait for it to become 0. If t becomes 0, that means everyone has reached the barrier. So initially, the semaphore has a value of n being equal to the number of processes that we want to synchronize with respect to the barrier. So the workers call wait. So t had the value of n becomes n minus 1. And then we call 0t. Now remember, 0, the operation 0 is only available with System 5 semaphores. And what does it do? It blocks until the value of t becomes 0. So every time that a new worker reaches the rendezvous point, the semaphore will be decreased by 1 more. The first worker will make it n minus 1. The second worker arriving to the rendezvous point will make it n minus 2, n minus 3. And the last worker to arrive to the rendezvous point will decrease it from 1 to 0, which means all the processes that had called 0 and they were blocked, all of them will continue together simultaneously. But unfortunately, 0 is a call that is specific to System 5 semaphores, and it is not available in POSIX. O da yok. Hay Allah. So this is an example of how to do it with System 5. Well, you can have a function called barrier wait, for instance. So this is the identifier for the sets of semaphores, the number of workers that are involved, num. Okay, so after you have initialized the semaphore to n, in this case, what do we do in this case? Yeah, so w num, z num, so we have two operations here, one for the wait and one for the 0 operation, wait t and 0t. For the wait operation, we will modify it by -1, just a single wait. And for the 0 operation, we are setting 0 so that it will be a 0 operation for the semop field of both of these operations, w and z. And then we call semop. Now, careful here, we do not want to execute them atomically together. We want to first execute wait and then execute 0. So we first call semop for the wait operation on our single semaphore. And if it is successful, then we call the semop for the 0 operation. It doesn't have to be atomic in this case. And that's it. Two distinct operations, one executed after the other. So can we do this also in POSIX? No, because we don't have the zero operation. So we have to do something different. What? With POSIX semaphores, well, you need some additional help. You need some additional variables in this case. And of course, you will need two semaphores, one for the barrier and one for the mutex. Why with the mutex? Because we have a certain variable, which is a shared resource. And while accessing it, we have to make sure that we are the only process accessing it. So that's why we need the mutex while accessing the count variable. Now, count is just a counter that keeps track how many processes, it keeps track of how many processes have reached the rendezvous point. Mutex is used in order to protect that variable. And the barrier is, well, for the synchronization barrier. So it is locked until all of the processes arrive there. So how is this going to work? Let's look at it. Now, each worker executes all of this. Now, first, it gets the lock in order to increment the value of the counter. Why? Because it has reached the rendezvous point. So initially, count is 0. So the first worker to arrive, it will get the mutex and increase the value of the count to 1. Okay, birinci işçi geldi. Count is 1. Then it checks whether count is equal to n. So basically, it is checking whether it is the last process to arrive to the rendezvous point or not. Randevu noktasına ulaşan son süreç miyim, değil miyim? So if count is equal to n, that means that is the last worker to reach that point. Now, if it is not, well, it is not. It is the first process to arrive. So count is equal to 1, not n. So the if will not work. Then it will call wait barrier. Now, wait barrier, but wait barrier, it will get blocked. Barrier is already 0. Okay, so the first process to arrive to the rendezvous point waits at wait barrier. The second one, well, the second one will also increase count to 2. It will check whether it is the last process to arrive. No, it's not. It will call wait barrier again. It is also blocked. And this will continue like this all the way until the last process arrives. Now, the last process to arrive to the synchronization barrier will increase count. It will become n. So is count equal to n? Yes, it is. That means you are the last process to arrive. So you will call post barrier. So now the barrier is 1. So one of the processes that has called wait will wake up. And immediately after waking up, it will call post barrier and continue. So that means another worker will also be able to wake up. And every worker that wakes up from wait, that gets unblocked, by calling post, also makes sure that the other workers can wake up after him. So that means zincirleme bir şekilde, in a cascade fashion, all of the workers, they will continue working after the synchronization barrier. That's the whole idea. Now, that's all for today. I believe there is a course starting in 1 minute. So thank you for your attendance. If you do not have a course and you have questions, I'm here available. And if you have to leave, you can send your questions by email. Thank you very much for being here. And those of you who have to leave now, I will see you tomorrow at 8:30. Those of you who remain can ask whatever questions you might have.
Excuse me, sir, is my